Alrighty. Good morning, guys. Can you hear me?
Yeah, we can hear you.
So there've been a few questions about how to use how to deal with these densities and joint densities, and how does one compute densities in terms of if there's a transformation of a random variable and you know what the density is of the random variable that's being transformed, how do you compute the density of the new random variable, and so on. And so I figured today we should spend some time going through a few examples about this, just to try to square it away. So that's my plan for today. I'll start by doing some examples about. So this is what I have in mind for today. We'll do some examples, two examples of density calculations. And then we're going to start on fixed income. And this is chapter 6. And I should also say that if you haven't signed up, sign up for a final slot. The schedule is on Canvas. About half the class is signed up, the other half is still missing. So I had originally thought we could have a final towards the end of the semester, but Anna says that this is not good and we should do it later. So the time's available, and you can find that on Canvas. And so when you send me an email, so this is just an email. Then I'll update the Canvas, and then. So what it means is that we have a little bit of extra time because we have that last lecture is not going to be consumed by finals. So let's spend some of that time going through some examples of these density calculations. This is really going to be relevant for 622 and 623. It is not relevant per se for the current class that we have here. And so what I did over the weekend was I updated the problem sheets. So let me just show you. Where are the problem sheets? Right, so I updated the problem sheets that I put out. There are lots of problems to work on. And I put in a few here at the end, problem 57, 58, and 59. This is what I've had in mind. This is similar to some of the things that have come up in the homework. And so I propose that we start out with 58 and then we do 59. So let's start out with number 58. And what you're given is you're given two random variables, x and y. They are independent. And so that's an important word, right? So the independent, and then the uniformly distributed between 0 and 1. Okay, so the uniforms on 0 to 1. And then there's a new random variable, v, and then you're setting v to be the ratio x over y. And then the question is, what is the distribution of v? Right, that's what we have. So you have x and y, the uniformly distributed, the independent, and v, that new random variable, is given as the ratio between two uniforms. Are there any questions on that? What we have here? Like, so what does it mean? Well, let's try to break it down. This here means that, for example, that the joint density of these two random variables is the product. of x's and y's density. And there are many equivalent ways of describing independence, but this here is one of them. What does it mean to be uniformly? What does it mean to be uniformly distributed on the interval 0 to 1? Well, that one means that the probability that x is less than u, and this probability here, there are three possibilities. It's x less than u, so if u is negative, so this is when it comes to be on this interval 0 to 1, something is happening here. It doesn't matter where you put the equality, but maybe I should put it, maybe I should put it like this, and then you have u in 0 to 1, and then you'll have u bigger than 1. And so the probability when u is small, right, if you're asking what is the probability that x is less than some number, that number is less than or equal to 0, well, then it's going to be a 0. And then u, that's what happens in between, right? And then when you're bigger, you're going to get a 1. And they're both uniformly distributed. So this here is the same as the probability that y is less than u. And you can, of course, based upon this, you can figure out what their densities is. But this is the distribution. This is a distribution, and then you can ask about the density. And so we need to know how we go from the distribution to the density. Well, that depends on, sometimes this is not possible, sometimes it's possible. It depends on whether or not there's a derivative. Here there is a derivative, so the density, so that will be the derivative. But this is going to be depending on what u is. So if you're less than or equal to 0, we're going to get a 0. If you are in between u 0 and 1, you're going to get a 1. Right? And if you're bigger, then you're 0 again. Right, so that what else do we have? We have joint density of x and y. This is the product. So what does that mean? Well, the joint density, that means that if I'm looking at the probability that the pair, say x over y, x comma y, belongs to some set, say A, I can perform that as a double integral over A, and then multiply into the density. So that will be, now it's the product. So maybe I should call this density, I could call this one here for fx of u. So it'll be the product, it'll be fx of u times fy, say v, du, dy, dv. So you take a set, A is some subset in R2. And then you want to know what is the probability that the pair x comma y belongs to this set. Well, you can get that probability by integrating out the joint density. And because of independence, the joint density is just a product. But of course, you can do something much more general. You can indeed go further, right? You can say if I take a function h of x comma y, you can calculate what this expectation here is simply by integrating over r squared of h of x, y, and then the joint density fx and fy, dx, dy. And here, h goes from R2 to say R. Right, so you can use the joint density for to calculate expectations, to calculate probabilities, but here we're given that they are independent. So the joint density is just a product of the two. The next problem is going to be a different story, but for now we have independence. Are there any questions on all the stuff that I've written here? I know some of you have asked me about this earlier, so I want to, if there are questions.
Yeah, can you explain the distribution? Like when U is greater than one, why is it one? I thought it would be zero.
No, but this is an increasing function.
Oh, okay. Yeah. Okay.
Right? The bigger U is, the bigger this number here is. Right. So it has to be increasing.
Okay.
It has to be over here to the left when U is small, it has to be small. And over here to the right, it has to go up to one. So here it's like it's zero, and then it increases linearly, and then it stays up here at one. Right. So bigger U's, as U gets bigger, the probability that X is less than a number that is getting bigger, that is going to be an increasing sequence of numbers, right? So it's going to converge up to one.
Okay. Yeah, that makes sense.
Right. So the density is a different story. The density is a different story, right? That one, we don't have properties like that. Here, what you need to have is you need to have that it's positive, and two, densities you need to integrate to one. So when I'm integrating over R of fxu, this better be one. And in this case here, the picture is going to be a zero here, and then you're one here, and then you're zero here. So this is not negative, this is non-negative, so we're good on that one. And when I integrate, I get this box here, this is a 1 times 1. So it's a 1.
Okay, cool.
Yeah, other questions? So what we're given is the density of X, we're given the density of Y, we're given that the independent, and now we want to know this ratio here. What about that one? And you can see, as soon as you take a ratio, right, a ratio is not a linear thing. So you're dividing by something here, and Y could be small, right? So when Y is small, divided by a small number, this could be huge. This thing here is bigger than 0, right? Because X and Y are both bigger than 0. But it's not like with the random variable X and Y themselves that these are bounded from above by 1. This thing here can be huge because when Y is small, when I'm dividing by something that's close to 0, this ratio is going to be arbitrarily large. So you will not have the same thing. Like you won't have just action, something interesting happening between 0 and 1. Something interesting here is going to happen on the interval from 0 and then onwards because Y, you're dividing by Y. So our job is to figure out what is going to happen here. And so I wanted to start by going through that. This here is an old exercise from a probability course I taught some years ago. So let's see what we get. So we're interested in the probability that V, right? So that's the random variable, that this is less than some little number V. And we only so when V is negative, right, this is equal to 0. So we want to consider V positive. So what's the probability that V is less than V? Well, we'll start by plugging in the definition X over Y. And then I know that Y is it's not negative, so I can multiply through. I'll get that X is less than Vy. Okay, so what I want to use is I want to use these formulas that I have up here. I want to know, because this here is just a function of X and Y, so I can express this thing here as an integral with respect to X's density and Y's density, which here, keep in mind, is the same, right? X's density is the same as Y's density because you're both uniform on the interval 0 to 1. Okay, so maybe to just make it even more, maybe to make it clear, like this A here is a two-dimensional set. So I should write something here in two-dimensional set. So I could write this as X. I could write this here as X takes values that are less than X is less than Vy, and Y takes values that are less than 1. Because Y is uniformly distributed on the interval 0 to 1, so I could do that, and I could do this. Okay, so now comes the time where I want to, so that's going to be, that's what I have over here. So I can express this two-dimensional, so the probability of this two-dimensional thing, X less than Vy and Y less than 1, I can express this as an integral of these densities. So let me do that. And I want to integrate, the first variable I want to integrate is over those Y's out here, because there's no connection between X's and Y's in the second term. So I want to have that one on the outer integral. So what I'll do is I'll write this here as an integral. This here is where I want to have my Y's. And they're going to be running from 0 to 1. And then on the inner integral, I want to have X's. So this is where I want to run my X's. I want to run my X's from 0 to Vy. And then I need the two densities, right? So I need my F. I need my F of X dx. And then I want to have my F of Y dy. So you can see here I'm using that the joint density of X and Y is given by the product. Like had it not been the product, I couldn't just separate them out like this. I would have to keep F of X next to F of Y, right? Because I cannot just stick this dx in the middle. So here we're really using independence. This here is because X is independent of Y. Okay. So I'm leaving here. So this is just a trick. So it's a good idea to leave the densities in for as long as possible. I don't want to start substituting in this 1 here too quickly, because keep in mind the density only lives between 0 and 1. Outside it's a 0. Outside it's a 0. So I'm going to be interested in the case like this Vy here. How does that compare to 1? So I could I could solve first just for a little calculation over here. I could be interested in, because I know that density f of x here, when x gets to be bigger than 1, this density drops to 0. So I'm interested in that particular y, that limit up here that is going to give me 1. And so if I solve for this, I'm going to get y is equal to 1 over b. So let me break that integral, the first one, when I'm integrating all my y variables. Let me run it from 0. Let me run it from 0 to 1 over v. And then let me put this f of y out there. And then the other integral, I'm just going to keep it to be the same. 0 to vy. And then fx. Right, and then the integral is dx, and then it's dy, right? So that was one part. And then the other part, I want to integrate. So this one here, these are my x's, this one here is my y. I want to integrate now. I have to go all the way from 1 over v to 1. So here I need to be a bit careful, right? Because I need to make sure that this 1 over v, for this to work, I need to have it to be between 0 and 1, because I'm breaking the interval from 0 to 1 into two components, right? I want to integrate from 0 to 1 over v, and then from 1 over v to 1. Right, so here, for this to work, I'm going to make the assumption that v that 1 is less than, I need the assumption that 1 over v is less than or equal to 1. So I need v here to be bigger than 1. Okay, so that this expression up here, it's going to be a couple of things. So this is when v is bigger than 1. Right, and there's going to be something else when v is less than 1 and positive, of course. Okay, so let me plug in the rest. Let me plug in the rest, and I'll have that 1 over v. This is between 0 and 1, so I could break the interval from 0 to 1 into two parts. I integrate up to 1 over v, and then from 1 over v to 1. Okay, fy, then I'll have the integral from 0 to vy f of x dx dy. This is when v is big, and then what happens when v is small? What happens when v is small? How far out will I integrate? V is small, so I would have to integrate. I would have to integrate from 0 to 1. Again, this is on my y's. This one here on my x. I'm integrating from 0 to 1. Integrating from 0 to 1. But now, how far out? I'll change this just in a second. Let me change this in a second, because what happens here in this case, 1 over v is bigger than 1. Right, if I divide through here by v, I'm going to get that 1 is less than or equal to 1 over v. So I have this term, and I know that the integral from 1 to 1 over v of f of y dy, I know that this is equal to 0, right? Because the density here, when I have a number sufficiently far out on the right, then density is dropping to 0. So there is no harm here at all in just integrating. There's no harm here in integrating. There's no harm here in integrating out to 1 over v there, because f just drops off. So whether I write 1 over v or I just write 1, this is the same. Okay, so here you can write 1, or you can write, it doesn't matter. Because the integrand, this is the benefit of keeping the densities in here. The densities, they drop to 0 on that last part. So you can write 1 here or 1 over v. So I got this broken up, and now I need to compute each term individually. And the benefit of breaking it up, like putting this, instead of integrating from 0 to 1, I'll integrate from 0 to 1 over v. What that does for us is that it tells me something about what this density is on the interval from 0 to vy. And now I can put a 1 here. There's also some, so what about this one over here? We had that discussion here. Let's continue with what happens now with a term like this one over here. Vy, how big is this number? You're integrating, y's are running from 1 over v to 1. So where's vy? So vy belongs to 1 to v. Right, so again, I can integrate all the way up to vy. That's perfectly fine. But on that interval from the density drops here to 0 at 1. So I don't need to integrate here from 0 to vy. I can also just integrate here from 0 to 1, right? Because vy is bigger than 1. Right, so I have a choice here. I can put 1 over v, or I can leave it as 1. Here I can put 1, or I can leave it as vy. Where it matters is that when I start substituting in what fx is, then it matters, because I need to know where my x's are, because I only get a 1 here when x's are between 0 and 1. So let me try to do that on the next slide. So if you're looking at the first one, so let me write out. So we're working in the case that v is bigger than 1. Then the first integral, those are my y's. This is from 0 to 1 over v if y, and then 0 to vy if x dx dy. So let me make sure we're good here. So when these here are my x's, this here is my y. So when x when x runs between 0 and vy, what is f of x? Well, it depends on what vy is, but here we're good because the y's you run from 0 to 1 over v. So here y's are between 0 and 1 over v. So vy is in this thing times v. So this is 0 to 1. That means I can put a 1 here. So this thing here, this is equal to 1. This one over here, v was bigger than 1, so this is also good. That is also equal to 1. So that integral here can become 0 to 1 over v, 0 to vy, dx dy. So this becomes an integral from 0 to 1 over v, vy, dy. That becomes v divided by 2, and then a y, and I need y equal to 0, and I need y equal to 1 over v. But it is right. This should be a square there. And so what we get is v divided by 2 times 1 over v squared minus 0. That was one integral. We also have the other one. We're looking at an integral from 1 over v to 1. This is where I'm integrating my y's. If y of y. And now I have a choice here. I can write vy of 1. Let me write 1 here. And then I have fx. Okay, so at least here I'm good. This is equal to 1. And v here is bigger than 1. So this number here is less than 1. So this is also equal to 1. So I can now integrate these two things out. I get an integral from 1 over v to 1. Integral from 0 to 1 of a 1, and then dx dy. This becomes an integral from 1 over v to 1 dy. This becomes 1 minus 1 over v. Okay, so all in all, the distribution, I have to add these two up. And this is when v is bigger than 1. So all in all, the probability that v is less than v, this is equal to, so when v is big, it's going to be equal to the sum of these two. So that is 1/2 1 over v. That was the first one, times, no, plus. That was the first one. That was this integral here, plus that one over here. So the second one was 1 minus 1 over v. And I think we can combine all this stuff. This is going to be 1 minus 1/2 times 1 over v. That was when it was big. What about when it's small? Well, when it's small, we have the second, we have to work on this expression over here. What is this thing? So here we can integrate either to 1 or to 1 over v. So let's do 1 over v. We're going to squeeze that calculation down here at the bottom. So we also need, this is when v is small. I'll integrate from 0 to 1 over v. 0 or 1 over v, which one do I want? I think I want 1. 0 to 1 of f of y. And then the next integral will be from, that'll be from 0 to vy. And let's just check, where is this number here? Well, when y is between 0 and 1, and v is less than 1, this here is between 0 and 1. So that's good. And what does it become? It'll be 0 to 1, then a density of 1, and then it's from 0 to vy. Density is 1, dx dy. Right, so that's the integral we had up, not quite, close. 0 to 1, vy, dy. This is v times 1/2. So that's the value that goes here. So this is the distribution function for the random variable v. Are there any questions on how to approach a question like this one? As you can see, I leave the densities in here for as long as possible. And the reason that I do that is so I can work on these bounds to get them to look right, so that when it comes time to substituting in the expressions for the densities, I know what the value is. Because outside these, so I'm shaving away these x's and y's for where the density is equal to 0. This is how I figure out how to break these intervals into smaller pieces. So that's the distribution, right? And then if you want the density, you compute the derivative. The derivative is going to be so the derivative, right? You have to compute the derivative. So the derivative here is going to be 1/2. And then over here, you have to compute the derivative of minus 1 over 2, 1 over v. But we can do that. Are there any questions on what we have here? So if I look at the derivative with respect to v of p of v less than v, like what would become? It'll be 1/2 here when v is small. And then what? It'll become 1/2 1 over v squared when v is bigger than 1. Right, so that's the density, and this is the distribution. Are there any questions on this question? That's not the case, and I want to do one where we play with the Jacobian. So let me just show you where you could read a bit about the Jacobian. So if I share a screen, where's my right screen to share? So here's Wikipedia. Here's Wikipedia. So it says something about the Jacobian and the determinant. And there are examples down here. So it's about transforming from 2D, from R2 into R2. The Jacobian, this is the matrix of the derivatives. And the one that we're going to be looking at today is this particular transform. This is the polar coordinates. So here's the Jacobian. It's this matrix here. He has computed the Jacobian to be R, right? So you take a determinant of this thing and take absolute value, then you're going to get you're going to get R, right? You take cosine times cosine, so you get cosine squared times R minus sine squared times R. Then you use that cosine squared plus sine squared is equal to 1, and you're left with R. So that's where this R here is coming from. That R you have here, this is the Jacobian. And so you need this Jacobian transform to go from one set of coordinates to a different set of coordinates. So here you have an xy integral. Over here you have an r theta, r phi integral. And so the Jacobian tells you something about substitution, right? So you're replacing x and y's with r's and phis. And the Jacobian is what appears in this. So you have to change the coordinates. That's one thing, but then you also have to multiply onto this this absolute value of the determinant. So let me try to write that down, how it looks like for us with densities. We're looking at problem number 59. And so what we're given is we have random variables x and y. And so what we do is we transform them with some function g, and this is going to give us new random variables that are called r and theta. Okay, so these ones here, d were given, right? And these ones here, they are new variables. Right, so these are given. So we know what their joint density is. Right, we know, so d given some joint density. Let's call it fxy, evaluated at some points, say a and b. Right, so d given some joint density, right? And then we get new random variables, r's and thetas, and we want to know what is that joint density for r and theta. Well, we should be able to express that joint density of r and theta in terms of x and y's joint density, and then the function g. Right, so what we're interested in the probability that r and theta belong to some set A. Right, so this is again two-dimensional set. Right, so A here is some set in R2. We're interested in this probability. Okay, so I'll write this here as the probability that g of xy belongs to, say, g of A. Belongs to A. I have moved the function. We'll do that next. Right, and then this function here, we're going to have that this is invertible. So we'll be able to write, so move g to the other side. And then we now want to use the property that you have a joint density. Right, so as soon as I have a joint density, I can compute these probabilities simply by integrating over the set of that joint density. Okay, so I'll do that. So this here is going to be an integral. What is the set? The set is this g minus 1 of a. And then the joint density, that was what we called fx a and b. All right, and then we integrate here with db, dA, say. And of course, what we want to be able to, we want to be able to get the, we want to be able to integrate here over set A, because if I can transform this, so the goal here is to write this as an integral over A of something, right? Because then what we want to have in here, let me call them du, dv, then whatever is going to appear here, this is going to be r and theta's joint density. Right. So I want to get the joint density out. That means that I have to be able to integrate just over the set A of something. So what is needed here is to get rid of that set. Instead of having g minus 1 of a, I want to have a down here. If I can put a down here, then whatever is going to appear as the integrand, that's going to be the joint density. So let me call that for f r theta of u and v. So that's the goal. And how would one go about doing it? Well, we do a substitution. Change of variables. So what kind of change of variables are we going to do? So change of variables. Substitution. What kind of a substitution are we talking about? Well, it's of course going to be something with that g up here. What we want to have is, we want to have the g of a, b. I want this to be my u's and v's. So here I'll have that my a's and b's, they are inside g inverse of a. Right, that's the interval I'm stuck with. A's and B's the inside here. So the substitution, does it work? Well, what is A of B? What is A of B? Well, this is going to be G inverse of U and V. So I have that, and then I apply G on both sides. So I get U, V, this is equal to so if AB belongs to G inverse of A, then UV belongs to A. Right, and that was what I wanted. I wanted this A freed up. I didn't want G minus 1 of A down here. I wanted A. And so it looks like this substitution here is going to do it. So if I do that substitution, this is why we need the Jacobian. So AB becomes G inverse of UV. So here I'll have to have f of x, y, and then instead of A of B, I need G inverse of UB. And then I need to multiply onto, and that was the tricky part, this is the Jacobian, by the determinant of the Jacobian evaluated at U, V. But this mess here, that's going to be my density that I'm looking for. Does that make sense? And in the specific example, in this specific example 59, let's have a look at it. What is being asked for. In 59, In 59, what you're given are two standard normally distributed random variables, x and y, and they are independent. So in 59, you're given that x is independent of y, they're both standard normal. And then the new variables, those are the polar coordinate representation. So you have that x and y, you're given as r cosine theta and r sine theta. So this here is my what was it we had here was, so you have, I go from x's and y's to r's and thetas through g. So here we're given, this is the inverse relationship, but this here is equal to g inverse of r theta. Right, that is giving me x and y's in terms of r's and thetas. So what the formula says is that the density that I'm looking at is going to be this thing here. It's going to be this thing here. So this, the FU, the FR theta density, according to what we had here, this is going to be that fx, y, and then you have to put the inverse in here. And then you need the determinant of the Jacobian. In absolute value. The inverse function, this was, first of all, they were given to be independent. So we can simply just multiply on to, we could just multiply the two individual densities. So this here will be, the first coordinate is r cos of theta. Then f of y of r sine theta. And then the determinant, that was the one we got from Wikipedia, or we can compute it ourselves. Remember what the determinant was for the polar coordinates. Like the determinant for the Jacobian determinant is equal to r. So that's the thing we have to plug in here too. So there's an r there. But this here was the determinant, the absolute value of the determinant, what is r? R is positive, right? It's the length in the representation. This representation here tells me when I'm thinking about an x and I'm thinking about a y, one way to think about these two would be as a length. So that's going to be my r. And then an angle, that's going to be my theta. So any point in R2, you can write either in its coordinates x and y, or you can write them as a length and an angle, and the angle is between 0 and 2 pi. So that's the new density you have there. We can plug in the normal density, like these fx and fy do a standard normals. So you get 1 over root 2 pi, and then you'd have e to the minus 1/2, and then this quantity in here is squared. So this will be r squared cosine squared. And then the same thing for this one over there. This is 1 over root 2 pi, e to the minus e to the minus 1/2 r squared sine squared, and then times r. And of course, you know that the exponential of a product is the sum of the exponential of the sum. So you get cosine squared plus sine squared, that is a 1. So you're going to get e to the minus 1/2 r squared times r. Right, so that is the joint density. That is the joint density of r and theta. Any questions on this? Those of you that had questions about this in the past, do we have any?
So both of these methods do like the same thing, right? Like 58 and 59.
Well, I mean, 58 was a one-dimensional problem.
Okay.
Right, there was this 58 here, you only had one random variable. But you're just asking to compute the density of this one random variable.
Mm-hmm.
Right, so there you, I mean, there could have been another one, right? You could also have had W, and W could have been like X times Y.
Mm-hmm.
And then you would have had to do this, the Jacobian again. The Jacobian comes when you're transforming a two-dimensional object into a two-dimensional object, right? That G here goes from R2 to R2. Right, so you have two random variables to begin with. You create two new random variables, and you want to know what is the density of that new pair in terms of the density of the old pair and the function you're using to transform it. What we did in the first one, it was similar, but it was one-dimensional. In the first one, we had two here. So the function, this ratio, that would not go into R2, that would just go into R. Right? That would go from R2, but then only into R. Other questions? So the formula you're seeing here, this is fairly general, right? You need to be able to invert this G here, and then you need to have the joint density of the original one. In our case, we were lucky because the original X and Y's, they were just independent, right? So that one here, this is because X is independent of Y, right? Then the joint density of X and Y is just a product. Had you not been independent, had there been some correlation, for example, then you would not be able to just take the product here. The last part of this problem, number 59, asks, like, so X and Y are independent. What about R and theta? Are R and theta independent? What about that? Are they independent? Well, we should check if f of r theta is equal to fr times f theta. If it's the case, then the answer is yes. If it's not the case, then the answer is no. So we now have the joint density. So what we could do is we could proceed as in question number 58 and compute the marginal densities for R and theta individually. But we already did a bulk of the work. So we have the joint density, and what we can do is we can just integrate out. We can integrate out one variable to get the marginals, right? So we can get, for example, if R of say A, we can get that out by looking at if R of theta of say A and B. And then what we do is we integrate out the other variable. I'll just try to do that. We have the density up here. We have the density up here. So we're integrating out the second variable. We're integrating out the second variable. This is the angle. That's my theta. So I'm only going to get something when the angle is between 0 and 2 pi. in that case, what do I get? 1 over 2 pi e to the minus 1/2 r squared times r, right? Outside that interval, this one here drops to 0. And so we need to know what this interval here is. So you, this is I'm messing up my a's and b's now. I should be more careful. Right? The first variable is a. So I did the same mess here, right? This is really horrible notation, right? I have u's and v's, and then they become r's down here. You shouldn't do that. We should keep them the same everywhere. It's just bad style to call this one for r and then my random variable for r. So I should do something else. I should call them u's and v's everywhere. I'm sorry. This here is my u. This is my u. This is my u. Like that theta there. This is not the random variable, right? This is my v. Mess. So now the first variable, this is my a. This variable, this is my a. And then I'm integrating respect to the second one, that's my b. So you see not much happens here, right? B doesn't appear inside, I just get 2 pi. This is e to the minus 1/2 a squared a. And this is valid for a positive, otherwise it's equal to 0. Right, and that's because the length of a vector, this is always positive. And then I do the same thing for the other one. So I do if theta evaluated at b is going to be an integral over r of the joint density. But this time I need to integrate with respect to the other variable. This is going to be with respect to dA. Okay, so where does A run? A runs, A is the first variable, so A is R, that is the length. So it's going to run from 0 to infinity. The same density, 1 over 2 pi. Excuse me. E to the minus 1/2 a squared times a and then dA. And now what's that integral? It's 1 over 2 pi. And then I need to find a function here that has this thing as its derivative. There's an a out there. This is minus e to the minus 1/2 a squared. I need to evaluate that at 0 and at infinity. Okay, so when I evaluate it at infinity, I'm going to get 0 and then 1. So this is equal to 1 over 2 pi. When is that good? What is b? B is my theta variable. B is my theta variable, so this is good for b between 0 and 2 pi. If theta b is equal to 0, when b is not in there. So this gave me formulas for marginals. And then what we want to see is, do we really have that the product of the two marginals is the same? So let's do if r of a times if theta of b. Well, this is going to be e to the minus 1/2 a squared a times, and then this 1 over 2 pi, and this is exactly f r theta of a and b. So the independent. This can seem a little bit surprising, maybe, that these two random variables, are in theta defined according to this formula that you get independence, but that's what you do. Are there any questions on what adjustment to? I'll put one more problem in there. Try it out yourself. This problem number 57. Let's see if you can get it to work. Are there any questions before we move on to fixed income? We all good? Well, I hope it helped a little bit. We went through a couple of examples here. There've been a couple in the homework, and as I said, there's one more sample problem up there on it. So the last big topic we're going to have is fixed income. So the big change, the new thing is stochastic interest rates. So before, this was an equity. Before, we had the money market account would just be the previous value it had times 1 plus R. So for fixed income, this is now going to change. The formula is going to look quite similar, but not quite the same. You still going to have this recursive structure. You started out at 1. Now the recursive structure is going to be 1 plus, and then this R here is going to become capital R, and then it's going to be R capital N minus 1. And this thing here is now random, where R N minus 1 is a random variable. So you should also contrast it with the stock. Contrast with, if you were to write down the same formula for the stock, the one that we've been writing is like this, and then you would have psi n here. Right, so for here, this is going to be Fn and not Fn minus 1 measurable. This one up here, this is going to be Fn minus 1 measurable. Right, so it's not like the stock where the return on the stock, like, so how do you go from Sn minus 1 to the stock price at the nth period? That involves this coin flip that you can't predict. Here with the money market account, the bank, it's different. The quantity that you're multiplying onto has this property that it is measurable with respect to the same place as what you're multiplying on. Whereas down here, this is not the case. This one here is measurable with respect to Fn minus 1, and this one here was only going to be Fn measurable. So it is random, but it's not as bad as this one here. And of course, as before, we can solve this recursion here. So as before, we can say that, well, the money market account starts out at 1. Then it moves on to becoming like 1 plus R0. This is S0. This is the value of the bank at time 1. Then the value of the bank at time 2. Well, this becomes well, the 1 plus R0, and then the next one. So you can see it's only S2 here that's going to be random. Now this here is random. This one here is F1 measurable. So S, the bank account's value at time 2, depends upon the interest rate over the first period and over the second period, but it does not depend on the interest rate over the third period. Right, and this is in contrast to what you had here. If you were to do this one, you get that S0, well, that's the first one. Then you're going to get S1. S1 is going to be S0 times psi1, and then you're going to get S0 times psi1, psi2. So you see the difference. It's true that we start out just being a constant, but in the value in the next period, already here you have randomness, but here there's no randomness. So this one here is like lacking a period compared to the stock. And this one here is F1 measurable, whereas this one here, this is F2 measurable. So that's the difference between the stock and the fixed income. We have this, you can predict what the interest rate is over the next period. You cannot predict what the return of the stock is over the next period. Any questions on this sheet? So as before, we have this recursive structure, but the new thing is that we have randomness in the bank account. So what that means is that you cannot any longer, you cannot move the discount factor we have typically been dividing by the bank account, right? So this is 1 over S0, say N. You cannot move the discount factor out of expectations, right? Because they're random. So we do not have that the expectation of 1 over S naught 0. This is strictly different than 1 over S0. Right, this one here, this is a constant. This one here, this is a random variable. So you cannot do that any longer. So that has caused problems in the past, but let me try. Let me try to. So we're going to look at some examples on that will show you that you cannot do this. So you start out with fixed income. So you start out for fixed income. You start out with a model for the interest rate, and then given such a model, you form. So you form. You don't form equity. You don't form the stock. What you do form instead is you form zero coupon bonds. So the basic building blocks in fixed income, they are zero coupon bonds. Right, zero coupon bonds. And you're not stock prices. So these zero coupon bonds, they're denoted by BNM. So the first entry here, this is current time. And then this one here, that's the end. This is the maturity time. This is a maturity where it pays off $1. So for a zero coupon bond, we've had them a few times before. For a zero coupon bond, right, there's this end time, which is here. The payoff comes at $1. And then what we're interested in is what happens at earlier times. So that will be your n equal to 0, n equal to 1, and then n equals to the expiry time. Like how much is this price? How much is this price? How much are these prices in here? At the end, it's $1, right? So we have that BMM is exactly 1. What we have here is B0M. Here we have B1M. And this one here is BMM. So the basic building blocks when it comes to fixed income analysis will be zero coupon bonds and not stock prices as we've been working with up to this point. Right, so we've been used to having randomness in the stock, and we've been used to that the bank account would just evolve with this interest rate that was constant, and it didn't vary. It did not vary over time, and it had no random component in it either. Now we're going to allow for stochasticity coming into the bank account through this interest rate here. So in these models, where you start out is creating the zero coupon bonds. These are going to be the basic. So when I say basic building blocks, these are the traded assets. And so our investor now, he can trade in the bank and he can trade in these zero coupon bonds. He can trade in the zero coupon bond that has all maturities, M equal to 1, 2, 3, and so on. So the first thing we need to do is we need to make sure that the model is arbitrage free. Right, so to ensure that there is no arb when trading, so it'll be the bank, it'll be zero coupon bonds, so BN1, BN2, BNM. Like the investor, he can trade in all of these. To ensure that there is no arbitrage when he trades in this thing, we need a martingale condition. What we need is that the zero coupon bond, when I discount it by the bank, I need this object here. This is a P tilde martingale. Okay, and what I have is that when n is equal to m, I know a 1 up here, right? So what I need is that if I look at the conditional expectation under the Tiller measure of b, say n plus 1 m divided by Sn plus 1, the bank account at time n plus 1, I condition on Fn. I need a martingale condition. I need this thing here to be Bn m divided by Sn. Okay, and so the way that we're going to do this, so this is the definition. We're going to do this by saying that BNM, this is how we're going to define zero coupon bonds. We're going to define this here as we're basically just multiplying over in this formula. This is Sn0 times the conditional expectation of what you have inside here, but all the way up to time m. So I'll put in here BMM divided by Sn0 given Fn, right? And this thing here, the top part, this is just a 1. And so of course you can move, this one here is already measurable, so you can move that measurable random variable inside. You move that one inside, and this here is going to be true for n equals 0, 1, all the way up to m. And the reason we do it this way is to ensure that this object is a martingale, and this is what will rule out arbiters. And you can see that it's a martingale because if I move this one here to the left-hand side, then that ratio is a conditional expectation, right? And conditional expectations are martingales. So let's just recall that argument. Like here, recall that the conditional expectation of a random variable A this is a martingale. Right? So remember how to do it. We will, what will we do? So let's call it Mn. Right, so we've done this a few times, but let me do it again. So if I take Mn plus 1 given Fn, and now what I do is I take the definition of Mn plus 1, plug it into this conditional expectation. And you're going to get E tilde of A given Fn plus 1, and then given Fn. And so we're in this situation where we have Fn and Fn plus 1 next to each other. And does anybody remember which one wins?
The F.
Say it again, Eddie, which one? F?
The Fn.
The Fn wins. Right, and that's my Mn. So this conditional expectation here, so remember, n here only sits outside. If there's an n in here, it does not work. So for zero coupon bonds, the random variable A is 1 divided by the bank account. This is 1 over SM0, and that does not depend. It does not depend on n, right? So we're in good shape. So this BNM discounted by the bank, this is a P tilde martingale. Any questions on this? So because I've seen this part here has been a challenge in the past. So let me try to write it out in some examples about how let me just maybe do some examples here. So if I look at B1, so look at B, if I take M to be 1, so a zero coupon bond that just expires in the next period, then what are we getting? Well, in that case, B01, according to the formula, this is a 1. Okay, so this is equal to the conditional expectation of, and then it'll be 1 it'll be 1 divided by, and then m here is equal to 1. So this is S0, 1. Condition on 0, if 0, so that's just the expectation here. And what we have here is E tilde of 1 divided by 1 plus R0. But remember the definition of the bank account is 1 would simply just be, well, the 1 that comes in from here, and then 1 plus R0. And this is not random, so here we'll have 1 over 1 plus R0. So the initial zero coupon bond is just the inverse. This is the inverse of S10. So now let's try to move it into m is equal to 2. So what is going to be my zero coupon bond? Well, I'll have the zero coupon bond expiring at time 2 will be given as E tilde, and it'll be 1 divided by S20. Okay, so we plug in what the formula is. So this is equal to 1 divided by, and then you have 1 plus R0 times 1 plus R1. And it's true here that 1 plus R0 was a constant, so we can pull him outside, but R1 is also stochastic, and he has to stay inside. So if I look at the inverse of S2, if I look at 1 over S20, this is going to be 1 over 1 plus R0 times 1 over 1 plus R1. These two are not the same. Like this one here is F2 measurable. This one here is F0 measurable. Right, so they're different. B02 is not given as the inverse of the bank account anymore. This is something that was true if you had interest rates that were not stochastic. Here, R1 is potentially stochastic, and you will not have this property. Any questions on this? If not, I had prepared a problem. This is problem number 15. So bring up problem 15. So problem 15. Okay, so here it is. Do we have all these things that are listed here? Do we have that you can multiply through like we have in question 1? Do we have that measurable at and these specific in these specific cases? So there are 4 questions here, and these 4 questions, they aimed at this issue that we're addressing, namely that there's a difference between the money market account and the zero coupon bonds. So for example, if you look at question number 3, do we just have that the zero coupon bond is the inverse of the bank account? Well, let's have a look at what we had on a piece of paper. Question number 3 asks, do we have that B0M is equal to 1 over SM0? And what's your answer to this question?
Yes.
What is it with these two here? Was this one equal to that one?
Oh, no.
So the answer is no here. What about question number 4? Do we have that B0M is always equal to its expectation of 1 over SM0? Well, then you take what you have here. Is it true that that one carries over? So is that true? Remember the definition. If I take n here to be 0, then the conditional expectation given f0, this is just the unconditional expectation. And then you have the bank account at time 0, that's equal to a 1. So then B0M is going to be equal to the expectation of 1 over SM0. So for question number 4, the answer is what do you guys say?
Yes.
Yes. Then there were more, right? So now there are trickier questions in there too. What about question number 2? Is B N M, is this object always F M minus 1 measurable? What do you guys say?
Yeah.
Yes, that's correct too. I remember the one. What could happen is to B N M is always F N measurable, right? Because B and M is this conditional expectation. So downstairs you have the bank account at the end, upstairs you have the bank account at the current time, and then you condition on Fn. Right, so this here is conditional on Fn, this is always Fn measurable. So this is, so for n less than or equal to m minus 1, we good? So the only one that remains is then what happens when n is equal to m. But when n is equal to m, I'll have that b m m this is equal to 1. And that also works. Right, because it's a constant. And then the last one is probably the most plausible one. So if we go to number 1, share the screen again so you guys can see it. Oh, there's the button. The last one is, can we decompose it like this? Do we have that the zero coupon bond that expires at time n plus 2 can be written as the zero coupon bond that takes you from time n to time n plus 1, and then from time n plus 1 to time n plus 2? What do you guys say? Is that true? well, don't be caught up in all the notation here. Let's just try to keep things straight. This thing here is conditional on Fn. So this one here is measurable with respect to what?
Fn plus 1, or n plus 2.
So BNM, right, we conditional on Fn. So this one here is Fn measurable, right?
Okay.
Right, so this one here is going to be what measurable?
Fn measure.
Yeah, and this one here?
Also Fn measure.
And this one here?
Also Fn plus 1 measurable.
So what do you think about the answer to the question?
It's not true.
It's not true, right? Because if I take an Fn measurable random variable and an Fn plus 1 measurable random variable, I take the product, what kind of a measurable random variable do I get?
An Fn plus 1 measure.
Yeah. And what is it on the left-hand side? It doesn't line up, right? This is Fn and this is Fn plus 1. They can't be equal. This problem here serves I'm trying to get rid of some of these ideas about, like, so you have a model where there's a constant interest rate. All these properties here, they hold. Now we're in a setting where we have stochastic interest rates. And not all these properties, they continue to hold. Like stuff like this is no longer true. So that's one reason why just with these stochastic interest rates, just be a bit more careful with because there's going to be randomness in places that didn't used to be random. So here you can pull out the top part because it's measurable, but you cannot pull out the bottom part, right? Because n is much smaller than m. So, and this is random, right? So he cannot go outside. That's not possible. Okay, I think it's time to take a little break. Are there any questions before we take a little break? Okay, then let's take a little break, and then after the break, we're going to do forwards.